Okay, hello and welcome back. In this video, we're covering section 10.3 on the ellipse. So we're continuing our exploration into the conic sections. So just to give a little bit of background and to define a few terms, let's imagine an ellipse. It's like a stretched out circle. And we could have different orientations. I'm drawing this one that's wider in the horizontal direction. But we could have a flipped version where it's wider in the vertical direction. But we'll have a center point, just like a circle. And we can split this ellipse into two axes. We have this one going through the center in the direction that the ellipse is wider. We would call this the major axis. And then the axis going through the center point, but on the shorter side of the ellipse, will be called the minor axis. And we'll have some terms. You can kind of think of it kind of like almost like the radius of this ellipse, except it'll be different depending on which part of the ellipse we're on. But this wider distance we'll call A. So we could describe that as the width of the major axis, or half of it, I suppose. And then this shorter distance we'll call B. So we'll need those for our definition of the ellipse, so we'll use those in a little bit. And then these corner points, so I can imagine 2 points on the edge here and 2 points on the edge here. These are what we'll call the vertices of the ellipse. So again, this distance from the center to the wider vertex we'll call distance A, and then this distance from the center to this shorter vertex we'll call distance B. So let's take a look at this definition, and we'll also introduce where our focus points will be. So we're defining the ellipse as the collection of all points in a plane, the sum of whose distances from two fixed points, called the foci, is constant. So let me draw another, maybe I'll use this circle tool, or one that's a little bit nicer. So let's see what they're describing. So we'll have our center point here. So our major axis would be the horizontal axis. And an ellipse will have two focus points, one on either side of the center point, and they will be on the major axis. So the focus points exist on the axis that is wider, on the wider side of the ellipse. So we can call this focus 1 and focus 2. So what they're describing is any particular point on this ellipse. So let's call some point over here. So they're saying the distance from these 2 points. So we can imagine one distance here and then a second distance here. The sum of these two is always the same for any point on this ellipse. So I can imagine another point down here. We would get two new distances. They would likely be different from our previous point, but if we add them together, we'll get the same value as we get when we added the two distances from our previous point. So we need to introduce one additional value, and that will be what we'll call C as the distance from the center to our focus point. So this would also be a distance of C. So let's take a look at the general definition, and I'm going to copy it from down here. This is the equation of an ellipse with the center at the origin, and the major axis is along the x-axis. So it would look something like what we have here. So the equation is x squared over a squared plus y squared over b squared will equal positive 1. It looks similar to the equation of a circle, except our x and y variables are divided by some values. And these are the same a and b values that are described here. So this number, if we take the square root of it, we'll get the distance from the center to the wider edge of our ellipse. And then this number beneath the y would tell us the distance from the center point to the shorter edge of our ellipse. And we're given this second part. So there's our equation. We're told a is greater than b because a is the major axis. And then we also get, they have it written as b squared equals a squared minus c squared. We could also write this as c squared equals a squared minus b squared. So this value c is the distance described here, the distance from the center point to the focus point. That's how we'll be able to identify where our focus point should be. So we'll need that piece, and then we'll use this definition as well. We'll get the same definition for an ellipse that is vertically oriented, where the major axis is the vertical axis. The equation will look the same. We'll just see a squared under y. The larger value will be under our y variable because it's stretched out wider in the y direction. You can view it from that perspective. So let's use these two. Let's look at a few example problems. I'll save the derivation maybe for another video. If you're curious, you can check out the textbook. They'll define how to get our equation for the ellipse. It comes from using the distance formula again, kind of similar to our description of the parabola. And then we can get this statement, c squared equals a squared plus b squared. If we imagine we're looking at a point directly above the center point and our two focus points, it produces an equilateral triangle where this would be our distance b, this is our distance c, and it ends up that this hypotenuse is equal to the distance a. It takes a little bit of an argument to show that that's true. But then from the Pythagorean theorem, we can get that b squared plus c squared equals a squared. And we can solve it for c. So c squared would equal a squared minus b squared. So we'll use that a lot whenever we're trying to find the distance to our focus points. So let's look at a couple examples to make this more concrete. So we're asked to find an equation of an ellipse with a center point at 3, 0, and one focus, oh, I'm sorry, the center point is at the origin, 0, 0, and the one focus point is at 3, 0. And then we're given a vertex location at -4, 0. So let's plot these just to orient ourselves to see what kind of shape we're looking at. So the center is at the origin, 0, 0. We have one focus point at 3, 0. So we'll have a focus point here. Every ellipse will have two focus points that are symmetrical on either side of the center point. So that means we should expect to have another focus point over there at negative 3, 0. And then we have a vertex at negative 4, 0. So that means symmetrically we should have another vertex point at positive 4, 0. So this will be our major axis. It's the axis that contains the center point and the focus points. We can imagine this will be the edge of our ellipse, but we need to find out basically how wide it will be in the vertical direction. And then we also want to build an equation. So from this information, we can tell that our A value, which will be the distance from the center to the wider vertex, is a distance of 4. So our A value will be 4. And then we're given the focus points, and we can see that the distance from the center to the focus point is 3 units. So that will be our C value. So since A is 4, C is 3, we want to find a B value because we're going to have an equation in the form x squared over A squared plus y squared over B squared will equal positive 1. So we already know A, we need to find B. So let's use that statement that C squared equals A squared minus B squared. Well, we know C and A, so we can say 3 squared will equal 4 squared minus B squared. So 9 will equal 16 minus B squared. If we rearrange this, I can say B squared will equal 16 minus 9, which is positive 7. And then when we take the square root of both sides, we'll take the positive square root for our B value. So just to look at the equation, we should get x squared over A squared. A is 4, so we'll see it as 16 plus y squared over B squared. B is the square root of 7, and we have B squared here as just 7. And this will be equal to 1. So there's our equation, but let's finish our graph. But it's helpful to see the equation. So that's our A squared term. The term underneath our x value, if we take the square root of it, that tells us how far to go from the center point to the right and to the left in the horizontal direction. So the square root of 16 is 4, so from our center we go 4 units to the right, that will be one vertex, and then 4 units to the left, and that will be our other. So under the y squared term, we have 7, the square root of that is the square root of 7. That's our b value. So that means we would go a distance of the square root of 7 above and below our center point. The square root of 7 is about 2.65. So between 2 and 3. 1, 2, 3. So we'll have some vertex point about here, 2.6, above the center point, and we'll go that same distance below the center point, about 2.6. That gives us the edges of our ellipse, so we can connect this to produce our graph. So again, the square roots of these numbers tell you how far to go to the left or to the right of our center point. That's the number below our x term. And then above or below the center point, and that's below our y term. And here we were given the center point, a focus, and a vertex, so we needed to use this information in order to find the missing b value. So that's where this second equation comes in handy. Okay, let's see another example. This time we'll be given the equation and we want to list its attributes and produce the graph. So we have x squared over 25 plus y squared over 9 will equal positive 1. So this will be our a squared term, and the 9 is our b squared. So let's go ahead and find c, that will be our distance from our center point to our focus points. We can say c squared will be a squared minus b squared. So c squared should be 25 minus 9. That will give us positive 16. So when we take the square root, we will get technically plus or minus 4. I'll just list the positive square root here. So with these pieces of information, we can actually already produce our graph and find our focus points. So this is in the form where our center point is at the origin. Our a value is positive 5, since a squared is 25. So that means I would go a distance of 5 units to the right. That will be one vertex, and then a distance of 5 units to the left. That will be our other. And then our b squared term is 9, that's underneath the y. So the square root of that is 3, which means that I would go a distance of 3 units above the center point. That'll be another vertex, and then a distance of 3 units below. So let's connect with the smooth curve. So rough sketch of our ellipse, and then let's put our focus points in. Our c value is 4, which means that we would go a distance of 4 units along the major axis, and that's the wider axis. So I would go 4 units to the right of the center point. So that'll be a focus point, and then 4 units to the left. I can call that F1 and F2. So let's list out our attributes. We said the center point is at 0, 0. The major axis, in this case, will be the x-axis, the horizontal axis. And the minor axis will be the y-axis, vertical axis. And we can list our focus points. One would be at negative 4, 0, and then our second will be at positive 4, 0. So even just given this equation, that's enough to produce the graph, but we can get the location of the focus points using the c squared equals a squared minus b squared formula. So we've seen two examples of a of a horizontal, like a horizontally oriented ellipse where the major axis is the horizontal axis. But we could have the other case where the major axis is along the y-axis. We get some vertically stretched object. Everything will look the same. Notice the equation looks the same except b and a are flipped. All this really means is that the larger value is beneath y and the smaller value is beneath x. That causes that vertical stretch because we will move a larger distance in the y direction. But if that's the case, that means our two focus points will then be on the vertical axis. So if we had our center point here, we would have a focus point above and below the center point. That would be another difference. So let's take a look at an example. This time we're given one that looks a little bit different. So we have 9x squared plus y squared equals positive 9. In our equations of ellipses, it's always equal to positive 1. So what we can do is divide everything in this equation by 9. We can take this number and divide everything. If this was some other number, we just divide by whatever number it is. That will produce a 1 on the right side. And then we'll start to see the more fraction form on the left side. So the 9's will cancel, and I'll write this as x squared over 1. Then we'll have y squared over 9 equals positive 1. So our larger number is underneath y. So that means it'll be vertically stretched more in the vertical direction. So that means I'm going to call 9 our a squared term, and 1 will be b squared. So that means a will equal 3, and b will equal positive 1. So here we can already produce the graph, and then we'll find our focus points. So our center is at the origin. We don't have a center point that's shifted yet. Underneath our x, we have 1. The square root of 1 is 1, so that tells me I would go a distance of 1 unit to the left and to the right of our center point. That will be our minor axis. And then underneath our y squared, we have 9. The square root of that is 3. That's our a value. So we'll go a distance of 3 above and below our center point. 1, 2, 3. We'd have a vertex here, and then a vertex here. So this will be our parabola, or I mean our ellipse. Now let's find out where the two focus points should be. So we know a squared and b squared. A squared is 9, b squared is 1. So we can say c squared will equal a squared minus b squared. So c squared will equal 9 minus 1. So that means c squared equals 8. And if we take the square root of both sides, we'll get that c is equal to the square root of 8, which reduces to 2 root 2. So that will be approximately, let's see, square root of 8 is 2.8. So that means we would go a distance of about 2.8 above and below the center point, since it's vertically stretched. So 2.8 will be pretty close to the edge here. So let's list these out as points. We have our center point at 0, 0. Our focus points, we would have 0, positive 2 root 2 as one point. That's this upper one. And then we would have 0, negative 2 root 2 as our lower point. And then our major axis, this time is the y-axis. And then our minor axis is the x-axis. So if you're given something like this that we started with, where it's not equal to 1, and we don't see any fractions, you can try dividing by this term on the right side. Just divide every term by that. That will give you a 1 on the right side, and we'll probably produce some fractions on the left. Just need to reduce it if necessary. Okay, let's look at one more where we're centered at the origin, and then we will shift to a more general center point. So we want the equation of an ellipse with one focus at 0, 2. We have vertices at the point 0, -3, and 0, 3. So that's all we're given so far. They don't tell us explicitly where the center point is. But let's see where these points land. So we're told we have a focus point at 0, +2. And then a vertex at 0, 3, and 0, -3. Oops, that's not where 0, 2 is. Let's go back. That would be vertically, so 0, 2. So a focus point here, and then a vertex at 0, +3, and 0, -3. So our center point should be in between the vertex points, because they should be symmetrical. So that does tell us that our center point would be at the middle, at the origin here. So that's one thing we can determine. And then the focus points are symmetrical as well, so that means we should have another one at 0, -2. And then this also tells us that our major axis is the y-axis, since the focus points are above and below the center point. So I can say the major axis will be the y-axis, so the minor axis will be the x-axis. So we can tell what our a value should be. That will be the distance from the center point to this one of these vertex points, which is a distance of 3. So a is equal to 3. We don't know what b is equal to, but we can tell our c value because that will be the distance from the center point to the focus point. So that will be a value of 2. So let's find out what b is equal to. C squared will equal a squared minus b squared. So that means that 2 squared will equal 3 squared minus b squared, or 4 will equal 9 minus b squared. If we rearrange this, we'll get that b squared will equal to +5. So then b will be the square root of 5. Which is about 2.24. So let's build our equation. We should be in the form x squared over b squared plus y squared over a squared will equal 1. So plugging in our values, we get x squared over 5, because b squared is 5, plus y squared over 9, because a was 3, will be equal to 1. And then let's complete our graph. So b is approximately 2.2. That will be the distance that we go from the center point to the edge of the minor axis. So about 2.2, a little farther than 2. So some point here, and then we'll go the same distance in to the left of our center point. So something like this. Okay, let's just make this a bit more general and define this where our center point can be anywhere. And this will be similar to what we did with our parabolas in our last section. So we really just need to introduce, instead of x squared over a squared, we can define it as x minus h squared over a squared plus, and instead of y squared, y minus k squared over b squared equal to 1. This is a case when we have a horizontal major axis. Because this is saying that the number beneath our x term will be greater than the one beneath the y term. And so our center point is at h comma k. And then if we have a vertical major axis, we'll just see the larger number beneath our y term. So technically I would call this b squared beneath x. And then we would have a squared beneath the y. This is for a vertical major axis. So we'll use the same process as we did before, where our a value and b value tells us the distance from the center point to our vertices. And then we can find c, and that's the distance from the center point to the focus points. So we'll either go to the left or to the right if we have a horizontal major axis. So to the left and to the right of our center point, we'll locate our focus points. Or if we have a vertical major axis, we would go above or below. So it just depends on how things are oriented. The text gives us a chart of our different possibilities. So our center point is at hk. If our major axis is parallel to the x-axis, meaning that it's horizontal, our focus point will be some distance of c to the left and to the right of our center point. So they describe that as h plus c, comma k, or h minus c, comma k. Whereas if we are parallel to the y-axis for our major axis, meaning that it's stretched in the vertical direction, we have diagrams here, then our focus point will have the x value from our center point, but it'll be some distance of c above or below the center. So I think it makes a little more sense visually here. This is our first case where we have a horizontal major axis, some distance of c away from our center point, to the left or to the right. And if we have a vertical major axis, we're some distance of c above or below the center point. So let's see a few examples. In example 5, we want to find an equation of an ellipse with a center point at 2, negative 3. We're given one focus point at 3, negative 3, and one vertex is at 5, negative 3. So what do we have? Let's start to graph some of these. Let's plot some of these points. So our center is at positive 2, negative 3. So down here, we have a focus point at positive 3, negative 3. So positive 3, negative 3 gives us a focus point. And then we have a vertex at positive 5, negative 3. So just from this information, we can actually already tell our C value and our A value. So the distance from the center to the focus, in this case, that's just 1 unit. That's our value C. So we can say that C is equal to 1. And then the distance from our center point to the vertex, and this is the one that's on the same line as the focus point, so that will be our major axis. So this should be our A value, will be 1, 2, positive 3. So we should also have a symmetrical focus point 1 unit to the left of our center point, and then another vertex 3 units to the left. So over here. So let's find our B value. So C squared equals A squared minus B squared. That means 1 squared will equal 3 squared minus B squared. So rearranging this, we get that B squared will equal 9 minus 1. So we get that B squared equals 8. Take the square root of both sides, and we get B is 2 root 2 again. Yeah, we saw that in a previous one. So at this point, we can build our equation. So it would be x squared. Oh, and we have a new center point as well. So I'll write out the general form first. It'll be x minus h squared over a squared plus y minus k squared over b squared equals 1. I'm putting a underneath our x term because we have a horizontal major axis. We can tell by the location of our focus points. They're to the left and to the right of our center point. So let's plug in 2 and negative 3 for h and k. So we would get x minus 2 squared. And then our a value is 3, so this would be a squared beneath that, positive 9. Plus y minus k squared, so we'll do y minus negative 3. That'll be our k value. The double negative will make it positive. So y plus 3 squared over b squared. We said here b squared is 8. And this is equal to 1. Sorry, something's weird on my computer right now. Okay. So that's our equation, and then let's just complete the graph. So our b value was 2 root 2. We said that was approximately, let me remember, square root of 8 is about 2.8. So we go a distance of about 2.8 above and below our center point. So 1, 2, so pretty close to the axis here. And then we'd be below about here. Okay, we got one more example, and then we'll see some applied problems. And this is a case where everything's all multiplied out. So we'll need to complete the square in order to turn it into a form that's more recognizable for us. So we're given 4x squared plus y squared minus 8x plus 4y plus 4 is equal to 0. So first let's group the x and y terms. I'll write it as 4x squared minus 8x plus y squared plus 4y plus 4. So normally we would need to complete the square on both x and y here. But if you notice y with that 4 attached to it, with the plus 4, this will already factor into a perfect square. This factors into y plus 2 squared. So there's no need to complete the square because it's already set up that way for us. For our x terms, we'll need to go through the completing the square process. But first, because of this 4 in front of the x squared, I'll need to factor that out and write it as 4 times x squared minus, in this case, it'll be 2x left over. So let's complete the square on x. I'll take this negative 2. It gets divided by 2 and then squared. So that's the process of completing the square. Negative 2 divided by 2 is negative 1. So negative 1 squared is positive 1. So that's the number that I would want to add inside of these parentheses. And we need to add something on the right side of the equation in order to balance this out. Since we introduced this 1, we need to add, in this case we wouldn't add 1 to the right side because technically this 1 is going to be multiplied by this 4 if we were to distribute it through. What we really added was a positive 4 to the left side and then factored the 4 out. So that means we need to add 4 to the right side. So we have to be careful. If we have this case where we have some number that was factored out, we still complete the square normally on what's inside. But when you add to the right side of the equation, you need to take that number and multiply it by the number in front of the parentheses. So now this will factor into 4 times x minus 1 squared, factoring this trinomial, plus y plus 2 squared, and this is equal to 4. So now let's divide everything by 4, so we'll get the equation equal to positive 1 on the right side. So if we divide everything by 4, it will cancel with the 4 on that first term. So I will write it as x minus 1 squared just over 1. Then we'll get y plus 2 squared over 4 will equal positive 1. So we divided everything by 4, and this is now in a form that we can read the center point and we'll be able to graph our ellipse. So the center point will be at positive 1, negative 2. So in the formula, if you remember in the general form we had minuses, so it ends up flipping the sign. If it shows up as a minus 1 in the equation, the center point would be at positive 1. And then we have plus 2 for the y. So the center point, it would show up as a minus 2. So we can already start to graph. So positive 1, negative 2 is our center. We can see that a squared will be 4. That's our larger number. A is always the larger one. And b squared is 1. So that means a is 2, the square root of 4, and b is 1. So from that, we can get the graph without our focus points yet. This means we would go a distance of 2 units above and below our center point. I go above and below because we're looking at the value underneath our y term. And then I would go a distance of 1 unit to the left and to the right of our center point, because that will be the square root of the number beneath our x term. So 1 unit to the left, 1 unit to the right. We get this little ellipse here. So let's get the rest of our attributes. We have a vertical major axis. Or we could say it's parallel to the y-axis. I'll just say vertical. The center point we found to be +1, -2. We can list the vertices. It looks like we would have one at 1, 0. There's one at 1, -4. Then we have two more, one at 2, -2, and one at 0, -2. And then let's get our focus points. So we know a squared and b squared. So we can say c squared will be a squared minus b squared. So c squared will be 4 minus 1. So c squared will be 3. We'll take the square root. C will be plus or minus the square root of 3. So that means we would go a distance of the square root of 3, in this case, above and below our center point, since our major axis is vertical. So we could get some decimal approximation, but we can just write it in this way. I can say the focus points will be, the x value will be +1. So we can start at our center point, 1, -2. And I just want to add the square root of 3. So that would be going above by a distance of the square root of 3. And then our second one, we could say 1, -2 minus the square root of 3. So above and below. So we have our equation. And then all of our attributes. Okay, let's see an example of an applied problem involving ellipses. So they show up in physics. The revolution of planets around our sun are in elliptical orbits. So they say ellipses are found in many applications in science and engineering. The orbits around the planets around the sun are elliptical, with the sun's position being at one of the focus points. They go on to say that stone and concrete bridges are often shaped as semi-elliptical arches, so some kind of archway. It's the top of an ellipse. Elliptical gears are used in machinery when a variable rate of motion is required. And it says they also have an interesting reflection property. It says if a source of light or sound is placed at one focus, the waves transmitted by the source will reflect off of the ellipse and concentrate at the other focus. It says that this is the principle behind whispering galleries, which are rooms designed with elliptical ceilings. So if we have some elliptical ceiling, we can imagine two focus points. If somebody is standing at one focus point and they whisper, well, the sound is going to reflect off of the boundary of the room and be all directed towards the second focus point. So if somebody was standing at that second focus point, they hear like an amplified version of the sound emitted from the first focus point. It's very interesting. So that's the basis of our question in example 7. It says the Whispering Gallery at the Museum of Science and Industry in Chicago can be modeled by the top half of a three-dimensional um, ellipse, which is called an ellipsoid. So we'll look at just a 2D slice. You can imagine something like this. Oops. The gallery is 47.3 feet long, so I can imagine this distance as 47.3 feet. The distance from the center of the room to the focus is 20.3 feet. So I can imagine the center point here. So we would have a focus on either side, and there would be a distance of 20.3 to the left and to the right. Actually, that would be farther out. So our two focus points. So it wants us to find an equation that describes the shape of the room, and it wants us to find how high is the room at its center point. So it's asking for this. This would be like our B term for the minor axis. So let's just set the center to be at the point 0, 0. I can say let the center point be at the origin. That'll make things a little bit simpler. So we want to find our b squared term, and then we also want to find the equation of our shape here. So we're given, well, let's see, what would be our a value? That would be half of this distance. If the whole thing is 47.3, we can just describe a as 47.3 divided by 2. So that means a squared, we would square that term, 47.3 over 2 squared. 47.3 divided by 2 is 23.65. So 23.65 squared. C squared, because we're given this distance from the center to our focus point, is 20.3. So that would be 20.3 squared. So let's find b squared, or let's find b. Well, I guess we just need b squared. So we can say c squared equals a squared minus b squared. So rearranging that, we can say b squared would be a squared minus c squared. So b squared will be our a squared term, 23.65 squared, minus c squared, so minus 20.3 squared. That gives us 147.2325. So let's build our equation. We'll have, this has a horizontal major axis, so it would be x squared over a squared plus y squared over b squared should equal c squared. So plugging everything in, this would be x squared over, let's see, a squared is 23.65 squared. Let's find out what that's equal to. 23.65 squared gives us about 559.3225 plus y squared over b squared. We said b squared was 147.2325. This will equal positive 1. So there's our equation, and then the height of the room, that's our b value. So our height should be the square root of b squared. So the square root of 147.2325. That's about 12.1 feet. Okay, that will conclude this section. So we looked at ellipses with the center point at the origin. We saw ellipse equations where the center point was at some general point hk, and then we saw that example of an application question. The main thing I would take away are these equations: x minus h squared over a squared plus y minus k squared over b squared equals 1. Or if we have a vertically, if our major axis is on the vertical axis, we would just swap a and b. So x minus h squared over b squared plus y minus k squared over a squared will equal 1. And then we've been using this other statement that c squared equals a squared minus b squared, where c is the distance from your center point to the focus, and then a and b tells you distances to the vertex points. So with these three pieces, we should be able to plot and graph ellipses and locate where their focus points are. All right, that'll be it for this video, and I'll see you next time.